Okay, so today we're going to do chapter 4. It starts with probability. We're going to assign probabilities to events, explain how the law of large numbers relates to relative frequencies, apply basic rules of probability to everyday life, and explain the relationship between statistics and probability. All right. When we use probability in a statement, we're using a number between 0 and 1 to indicate the likelihood of an event happening. You're So this is always amusing because if you've taken Math 118, or if you end up taking Math 118, which is the financial business math, you will hear me kind of harp that you don't always have to stop a percentage at 100%. You can have over 100% in certain situations. Obviously, grades are not this one of those, and typically you will never have a probability between anywhere else except for 0 and 1. So it's literally 0% of a chance or 100% of a chance and anything in between. Okay, you're not going to, if it's over 100% or if it's over 1, then it just means that the likelihood of it happening is it will happen. So I don't know, the examples of it are kind of hard, but all right, probability is a numerical measure between 0 and 1 that describes the likelihood that an event will occur. Probabilities closer to 1 indicate that the event is more likely to occur. Probabilities closer to 0 indicate that the event is less likely to occur. P of A, I don't know how to read it any other way to you except for how it's read, denotes the probability of an event A. If P of A equals 1, then event A is certain to occur. If P of A equals 0, then event A is certain not to occur. So the likelihood of a mass population concert happening in 2021 is probably closer to 0 than it is to 1. Okay. Doesn't mean that it won't happen, but probably not going to happen this year. All right, probability assignments. A probability assignment based on intuition incorporates past experience, judgment, or opinion to estimate the likelihood of an event. I don't necessarily know if I include that into my probability assignments. I basically go off of the numbers. If I guess intuitively, if you look at a frequency and you don't agree with it, you could always raise the question, but more than likely, if you have the data to back it up, then you're doing it correctly. A probability assignment based on relative frequency uses the formula probability of an event equals relative frequency, which is the frequency divided by the number n in the sample. Okay. A probability assignment used on equally likely outcomes uses the formula number of outcomes favorable to the event divided by the total number of outcomes. These are basically the same. It's just different wording. And this one obviously will come from a frequency table. This one you may have to actually count out given what information you might be given. So like you may end up having, someone might ask you, what's the probability of getting heads if you toss a coin 100 times? And that might be literally the only statement they give you. So you can either choose to say, well, it's probably 50% of the time, or you could sit there and you could take a coin and you could toss it 100 times. And then you can count up all the heads that you got. So it'll just depend on what WebAssign wants you to do. I don't believe they ever actually have you flipping coins 100 times, but you never know. Now you know how to do it if you have to. Okay, so this example says, consider each of the following events and determine how the probability is assigned. A sports announcer claims that Sheila has a 90% chance of breaking the world's record in the 100-yard dash. I don't know why it just randomly gave you that solution there. Kind of wish it wouldn't have. But so yes, is there anything, do you feel like there's anything that this sports announcer probably looked at before he made this claim? He could have potentially looked at past stats on the 100-yard dash, but more likely than not, he's just a really big fan of whoever Sheila is, and so that's why he made the claim. All right. Obviously, we all know that we're not going to get our statistical, I guess, like our personal sports preferences are not going to always come or not going to always agree with sports announcers, right? I'm sure there's some sports people that the announcers totally rag on that might be one of your favorite athletes. So, okay. Let's keep going. This situation is saying Henry figures that if he guesses a true false question, the probability of getting it right is 50% or 0.50. Says in this case, there are two possible outcomes. He's either correct or incorrect. Since Henry is guessing, we assume the outcomes are equally likely. There are n equals 2 equally likely outcomes and only one is correct. So by formula 2, number of favorable outcomes divided by total number of outcomes would be 1/2. Wow, that's really, really, really blurry, which is 0.5. Yes, for a true or false, that's the only thing you can have. That would not be the case for what kind of question? Would all test questions have a 50-50 chance?
No, this would differ if it was a multiple choice question or a written answer.
Yes, both of you are correct. Celine put in the same thing in the chat, and Tucker, you're correct. So the way it kind of works is what you typically see are 4 answer option choices if it's multiple choice. Sometimes I believe on the SAT you have up to 5 answer choices, so that probability would also change. All right. C here says that the Right to Health lobby claims that the probability of getting an erroneous medical laboratory report is 0.40 based on the random sample of 200 laboratory reports, of which 80 were erroneous. So they took 80 and divided it by 200. Again, I apologize that that's so blurry. And they were able to say 0.40. Now, here's something you have to keep in mind. If this apologies, that hit my computer. If this Right to Health lobby is pro or against something, then you also have to maybe consider where are they getting this sample from. So are they getting it from a known source that maybe isn't as accurate as other locations? Or is it truly random sample and it's coming from a slew of different locations? So you just kind of have to be aware of who's presenting you the data and what do they really want that data to be telling you. Okay. All right, what is probability? Probability is the technique of using relative frequency of an event, as the probability of that event is a common way of assigning probabilities and will be used a great deal later in later chapters. The underlying assumption we make is that if events occurred in a certain percentage of time in the past, they will occur about the same percentage of times in the future. In fact, this assumption can be strengthened to a very general statement called the law of large numbers. Okay. So, law of large numbers. Basically, it says the sample size increases and increases, the relative frequency of outcomes get closer and closer to the theoretical or actual probability value. So the law of large numbers is the reason businesses such as health insurance, auto insurance, and gambling casinos can exist and make a profit. No matter how we compute probabilities, it is useful to know what the outcomes are possible in a given setting. So in theory, a casino would have too much risk to actually work. But we all know that there are gamblers out there that don't really care what their risks are or what their bank account are, and they're just going to go and do what they're going to do. So it's a sad world, but that is the case. And as long as people keep coming through the doors, casinos will continue to make a profit. All right. For instance, if you were going to decide the probability that Hard Scrabble will win the Kentucky Derby, you need to know which of the other horses will be running. To determine the possible outcomes for the given setting, we needed to define a statistical experiment. So what's important with the statistical experiment or statistical observation? An event is a collection. So you have to have an event, which is a collection of one or more outcomes of a statistical experiment or observation. A simple event is one particular outcome of a statistical experiment. The set of all simple events constitutes the sample space of an experiment. So if you had the time, and I don't even know right now if they're really up and running, but if you had the time and you went to a casino and you watched the horse races and that's all you did. You just watched and you recorded the winners. I don't know, first, second, third of every race. You wrote down all the horses involved in each race. You could then theoretically predict the winner after you had enough data values. Okay. We are not going to get into how we can predict winners in this class because I am not all about that slippery slope. All right. I have way too much of an addictive personality for us to go down that very scary road for me. All right, using a sample space. Human eye color is controlled by a single pair of genes, one from the father and one from the mother, called a genotype. Brown eye color, B, is dominant over blue eye color. I believe that's supposed to be a lowercase scripted b, but it just looks like an L. Therefore, in the genotype, I guess we'll go with B lowercase b, consisting of one brown gene and one blue gene. The brown gene dominates. A person with the BL genotype gets brown eyes. If both parents have brown eyes and have the genotype, what is the probability their child will have blue eyes? And what is the probability their child will have brown eyes? Okay, so think about that for a hot second. And then we're going to go over it. Okay, so if you haven't taken biology at this point, or if you are thinking about taking a college level biology, this will come back around. You will have to know it, and you will have to know it very, very well. And with many, many other genotypes than just eye color. Okay, so here's from the father. Here's options with the father and mother together. And you can see we have 4 different typings there. All right. According to the genetics theory, the 4 possible genotypes for the child are equally likely. Therefore, we can use Formula 2 to compute the probabilities. Blue eyes can occur only with the genotype, so there's only one outcome favorable to blue eyes. Okay. So I guess they're not going to give you the percentage, but if it's 1 out of 4, then you know that's 25%. So in theory, the second one should be the converse, and it is 3/4. Okay. How did we know that? Well, we know that because the 2 together have to equal 1. So if the first one was 1/4, the second one has to be 3/4. All right. The sum of probabilities of a simple event in a sample space must be equal to 1. We can use this fact to determine the probability that an event will not occur. For instance, if you think the probability of 0.65 that you will win a tennis match, then you have to also assume the probability that you will lose is 0.35. These events are known as complements of one another. So you have event A, and then if event A does not occur, we call it the complement of A. And it's basically a capital A with a little c. All right. Those will be on your exam. They will definitely be in your homework. All right. Okay, so here you can notice that if they asked it in another way, we would have event A, blue eyes, complement of A would be brown eyes in this case because they make a sum of 1. The complement of A is the event that A does not occur. A complement designates the complement of A. Furthermore, the probability of A, or P of A, plus P of the complement of A is equal to 1. Right? You can also have the inverse, which is basically saying that the probability event A does not occur would be the probability of A complement, which we can find by taking 1 minus the probability of A. Now, this might just seem random to you and like you won't really need it, but sometimes you're asked to find the complement and the only thing you know is the probability of A, or you know how to find the probability of A given the information you know about A. So once you find that, then you know you can subtract it from 1. All right. So it may seem rather easy at this point and kind of a no-brainer, but once you have some of the problems in front of you from the problem sets, you're going to want to know this information. All right. Complement of an event. The probability that a college student who has not received a flu shot will get the flu shot is 0.45. What is the probability that a college student will not get the flu shot if the student has not had the flu shot? So not getting it would be the complement. So you have to take it away from 1. Okay. So you take 1 minus the probability of someone getting the flu shot. And then so 1 minus 0.45, so then you get 55% will not get the flu shot. I can guarantee you those stats are very different this year. Probably more like 100% of people got the flu shot because that was the only thing they could get. Right? We can often use Venn diagrams in mapping like this to kind of help you visualize what you're working with. It's not so much necessary when you're working with a simple case like this, but eventually you're going to have different samples and different populations, and having something kind of like this to just kind of get your brain around everything that's going on can be beneficial to you. All right. Any questions on like the idea behind probability? Like that was just barely touching the surface. Okay. All right. Probability related to statistics. So when we think about probability, it's basically how we communicate to people who don't understand statistics. It's basically how we get them to understand what we're talking about. A lot of times when people don't like math or don't like stats and don't understand stats, they can at the very least understand probability. Okay? So that is a very nice and simple relation there. Probability is the field of study that makes statements about what will occur when samples are drawn from known populations. Conversely, statistics is the field that describes how samples are to be obtained and how inferences are to be made about unknown populations. Okay, so if we look at this, which if I were you guys, I would definitely either write this down or come back to the video later or take a screenshot. So if we look at the example of a probability application, the condition we're given is we know the exact makeup of the entire population. So the example they're saying here is given 3 green marbles, 5 red marbles, and 4 white marbles in a bag, draw 6 marbles at random from the bag. What is the probability that none of the marbles are indeed red? Okay. An example of a statistical application is saying we have only samples from an otherwise unknown population. And the example says draw a random sample of 6 marbles from the unknown population of all marbles in the bag and observe the colors. Based on the sample results, make a conjecture about the colors and number of marbles in the entire population of all marbles in the bag. Okay. Do we kind of see the difference there? In one situation, we know exactly what's going on, and you can definitely pull a marble out, see if it's red. Pull a marble out, see if it's red. But we know once we hit 5 marbles, there are no more red marbles. Okay. In the second situation, we can pull out 5 marbles or 6 marbles, and we could still have red ones in there. In theory, the whole bag could be red. All right. We just don't know. All right, that is the end of, is it not? Yes, it is. That is the end of section 4.1. Any questions on 4.1 before we switch gears to 4.2? Probably the same basic gear, but a little bit more info. No? Okay. If you are one of my students who likes to take handwritten notes, this will be the section to take the notes. Okay. So we're going to talk about some probability rules and compound events, right? We're going to compute probabilities of general compound events. We're going to look at probabilities involving independent events or mutually exclusive events and use survey results to compute conditional probabilities. Definitely something that's going to be on your next exam. Definitely something you want to pay attention to. Okay. And definitely practice with your homework. Independent events. 2 events are independent if the occurrence or non-occurrence of one event does not change the probability that the other event will occur. We use the multiplication rule for independent events, and we read it as P of A and B can be found by taking P of A times P of B. Okay, so let's think about this in terms of an example. Independent events. So if we have event A and event A is walking your dog, and event B is getting an A on your exam, are those 2 dependent upon each other? Does you being a good pet owner and walking your dog have anything to do with if you're going to get an A on your exam or not? No, they're independent of each other. Okay, so if you can say that yes, the events are independent of one another, then you can use the multiplication rule for independent events. However, if you have a dependency, we will have to go out it a different way. An example of a dependent event would be, the easiest one that I can say would be if you study for 10 hours in 1 week, will that have an effect on the grade you get on your exam? Right? The number of hours you put in studying will have an effect on your exam one way or the other. It's either going to help you or could potentially hurt you, but they're connected. Okay? If the events are dependent, then we must take into account the changes in the probability of one event caused by the occurrence of the other event. The notation P of A given B denotes that the probability of event A will occur given that event B has occurred. This is called a conditional probability. Okay. We read P of A given B as the probability of A given B. If A and B are dependent events, then probability of A is not equal to the probability of A given B because the occurrence of event B has changed the probability that event A will occur. So if we look at this general multiplication rule for any events, you can see that we have a little bit of a difference here, right? You have probability of A times the probability of B given A, and you have the probability of B times the probability of A given B. They seem rather silly to write out, but once you have different examples, you will see why. Okay. We will use either formula 5 or formula 6 according to the information available. Formulas 4, 5, and 6 constitute the multiplication rules of probability. Okay, so if you are making a flashcard, air quoting, flashcard, large sheet of paper, whatever you want to say it, the multiplication rules of probability are those 3 formulas, 4, 5, and 6. Make sure they're in the same area so that you can use them. I would definitely suggest if you go through your homework and you're using one, you might want to write that example down on your note card. Okay. They help us compute the probability of events happening together when the sample space is too large for the convenient reference or when it is not completely known. Note, for conditional probability, observe that the multiplication rule can be solved for P given A leading to this. Okay, so P and the probability of A and B divided by the probability of B, given that the probability of B is not equal to 0. Okay. You can write that down if you want. Your algebra skills should be able to get you there either way. Okay. Whether you write it down or not. All right, let's look at an example. Suppose you are going to throw 2 fair dice. Why do you think it's important that they're telling you the dice are fair?
To ensure an entirely equal outcome.
Correct. Okay. If you're going to give me an answer and it's dealing with dice, you want to make sure you put the word fair in it because I'm going to ask you, how do you really know that? Okay. What is the probability of getting a 5 on each die? All right. So the 2 events are independent. So we would use formula 4. Why are they independent? Why do you think they're independent? We're rolling these 2 die, right? Now, nothing says that we have to roll the die at the same time. So we can roll die 1 and then we can roll die 2. And that is why it's independent, because there's nothing that die 1 can do. There's nothing that die 1 can land on that will have an impact on what die 2 can give as a result. Okay? They're independent of one another, right? It's not like the question saying, what's the probability of getting 5 on each die, but once you roll die 1, you have to exclude that result from the second die. Okay, that's not what they're saying. So, what's the probability of getting 5 if you roll a 6-sided die?
One-sixth.
1/6. Good. So it's obviously going to be 1/6 and 1/6. So we should get 1/36. Yep. Okay. All right. Here is another kind of option you can use. By the way, this might be in your textbook. It probably is, figure 4-2. If someone reminds me via email, I will email out to you this grid. You might think it's silly for me to send it out to you, but you have no idea how many questions you will get that involve rolling 2 dice. So if you already have all the outcomes listed, sometimes it saves you a little bit of time. Okay. And I have no problems with you guys using tables like this. All right. You can also see here that we have 36 options, right? So this is the outcome we want, 1 out of 36. All right. And we're good with that. Okay, how to use the multiplication rules. First, determine whether A and B are independent events. All right, if they are independent events, then if A, probability of A is equal to A given B, then the events are independent. If A and B are independent events, then we can do the probability of A and B, and we can multiply probability of A times probability of B. So these are just all 3 of your forms together. Okay. So remember when I said you should write them all in one place? This is you writing them all in one place. All right. I'll give you guys a few more seconds to write that out. Okay. All right, addition rules. One of the multiplication rules can be used anytime we are trying to find the probability of 2 events happening together. Pictorially, we are looking for the probability of the shaded region. All right. A and B. Again, this is an example of a Venn diagram. They come in very, very handy, even though they are rather simple in nature. They give you an idea of what is going on with your problem. Another way to combine events is to consider the probability of one event or another occurring. For instance, if a sports car saleswoman gets an extra bonus if she sells a convertible or a car with leather upholstery, she is interested in the probability that you will buy a car that is either a convertible or has leather upholstery. Of course, if you bought a convertible with leather upholstery, that would be fine too. All right. So pictorially, the shaded region in figure 4.4b represents the outcome satisfying the OR condition. All right. So I don't shade mine in except for what I'm interested in. So I guess in this case, what they're saying is that they're interested in either the leather upholstery or the convertible or the space that has both, and then the rest are the other cars that you and I can afford, right? And notice that the condition A or B is satisfied by any one of the following conditions. Any outcome in which A occurs, any outcome in which B occurs, or any outcome in where both A and B occurs. It is important to distinguish between the OR combinations and the AND combinations because we apply different rules to compute their probabilities. Okay. Once you've decided that you are to find the probability of an OR combination rather than an AND combination, what formula do you use? It depends on the situation. In particular, it depends on whether or not the events being combined share any outcomes. So let's look at two situations. Consider an introductory stats class with 31 students. The students range from freshmen through seniors. Some students are male while others are female. Figure 4.5 shows the sample space of the class. So we have so many female freshmen, so many male freshmen, so many female sophomores, so many male sophomores. You're getting the idea. Okay, so here is your sample space for the stats class. And once you now to find, suppose we select one student at random from the class. Find the probability that the student is either a freshman or a sophomore. Okay, so we come back over here. We have 15 students that are freshmen and 8 students that are sophomores. But we know we have a total of 31. Okay. Probability freshman or sophomore, we're going to take the probability of freshmen plus the probability of sophomores. We'll get the probability of them combined. Now, that was nice because can you be a freshman and a sophomore? So it's a very tricky question because the answer technically is yes, you can be both a freshman and a sophomore. Here's where it gets tricky. In theory, when we say freshman, we mean one's first year in high school or one's first year in college. Some students failed their freshman year. So in theory, they must repeat their freshman year. However, you can also be a sophomore, but only have credits enough to be a freshman. Okay, so that's why it's kind of confusing. For the purposes of this class, if you see the word freshman and you see the word sophomore, junior, and senior, you know that they are different. Okay, we're not going to go down the rabbit hole of they could well be technically both. All right, so that is why we can do it this way. Let's look at another example. Notice that we can simply add the probability of freshman to the probability of sophomore. No student can be both a freshman or a sophomore at the same time. Again, that is in a utopian world. Okay. Select one student at random from the class. What is the probability that the student is either male or female? So if we come back here, someone count out how many females we have and someone count out how many males we have. What do we end up getting?
$17 female, $14 male.
Okay. So if we have that, oh, there's your decimal. Sorry, didn't see it. Okay. Oh, it was from the sophomore class. My bad. That's all right. If you were doing it for the total, we would use those numbers. Okay, so probability of sophomore is 8 out of 31. Probability male is 14 out of 31. Probability male and sophomore is 5 out of 31. If we simply add sophomore and male, we're including sophomore and male twice to the sum. To compensate for this double summing, we must simply subtract probability of sophomore and male from the sum. All right, are we following along with that? If we counted up males and females, which we did do, And then we care about the males out of the sophomore class. We have them twice, okay? So that is why we have to do the subtraction. All right. Now, the other way to look at it would have just been counting. Instead of doing this, you could have just counted. Okay. We say that events A and B are mutually exclusive or disjoint if they cannot occur together. This means that A and B have no outcomes in common. And so another way of looking at it would be A and B, the probability would be equal to 0 because one or the other has to be 0. So then we end up getting 0. Two events are mutually exclusive or disjoint if they cannot occur together. In particular events, A and B are mutually exclusive if the probability of A and B is equal to 0. Formula 7 is the addition rule for mutually exclusive events. So if we have the probability of A or B, then it's going to be equal to the probability of A plus the probability of B. Okay. I assume we're going to get an example on this. If the events are not mutually exclusive, we must use a more general formula for 8, which gives the general addition rule for any events A and B. And here we already used that in the last example. Probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. Okay. All right, procedures. I think you guys understand this at this point. First, you have to determine if A and B are mutually exclusive or not. And if the probability of A and B is equal to 0, then you would have mutual exclusivity. If they are mutually exclusive, then you have the probability of A or B is equal to the probability of A plus the probability of B. If A and B are any events, then you have the probability of A or B is equal to the probability of A plus probability of B minus the overlap. Okay. The Venn diagrams extremely help you out understanding really what's going on and when you add versus when you subtract, that kind of thing. My question to you, if you ask me to help you solve a question on the homework, is going to be, if it's applicable, did you try looking at a Venn diagram and figuring out what you need to pull out versus what you need to include, right? So let's look at this example real quick before we move on to 4.3. Laura is playing Monopoly. One of her next moves, she needs to throw a sum bigger than 8 on the 2 dice in order to land on her own property and pass go. What is the probability that Laura will roll a sum bigger than 8? So first question is, we have 2 dice. So then that's a total of what? A highest possibility of 12. And you need a sum bigger than 8. So you're looking at 9, 10, 11, and 12. Which are all possible to get on two dice if you're adding them up. So these outcomes are mutually exclusive since only one of these sums can possibly occur on one throw of the dice. The probability of throwing more than an 8 is the same as the probability of 9 or 10 or 11 or 12. Since the events are mutually exclusive, we can go ahead and add them. All right. If you roll and get a sum of 9, it doesn't mean you also rolled and got a sum of 10. All right. They're not together. So that also means that the reason why you see this 4, 3, 2, 1 at the top is because you need to roll a 9 in order to roll a 10, in order to roll 11, in order to roll a 12. So you have 4 ways that you can roll a 9, right? 3 and 6, 4 and 5. What else can we have? Nope. And then the opposites of those. And then you have to figure out how to get 10 and how to get 11. And then obviously 12 is only 6 and 6. That's it. All right, you add them up and you don't forget that you want to reduce. So if you're answering a question in WebAssign and you're getting the answer wrong, it might be because you didn't reduce. Also, I'm not really sure if you guys can always see it, but I know when there's the Ask the Professor, I always see little hints written in red. So read the little hints. They might help you. All right. Again, look at our nice little chart that we're getting in 4.2. Right? You can literally go through here and you could count the ways that you can get a total of 9. Here's 1. Here's 2. Here's 3. Here's 4. Here's 1 for 10, 2 for 10, 3 for 10, 1 for 11, 2 for 11, 12. All right. That little die chart really helped you out. There are 36 equally likely outcomes for this example. Those favorable to 9 are 6 and 3, 3 and 6, 5 and 4, and 4 and 5. So P of 9 is equal to 4 out of 36. The other values can be computed in a similar way. All right. That is it for 4.2. We're going to keep on trucking and get the last section in. Okay, so I find the trees and counting techniques to be a little bit easier to understand and kind of grasp a little bit more so than the adding and multiplying probability options. So if you wanted to do homework 4.3 first, I wouldn't have a problem with that. I think it would be smart for you to do the easier one first. Organize outcomes in a sample space using tree diagrams. Compute number of ordered arrangements of outcomes using permutations. Compute order of non-ordered groupings of outcomes using combinations. Explain how counting techniques relate to probability in everyday life. When outcomes are equally likely, we compute the probability of an event by using the formula, and that's literally what you all should be used to doing by now. Number of favorable events for the event A divided by the overall number of outcomes from the sample space. Okay, so that's just kind of like a review of what we talked about before. The tools we present in this section will help you count the number of possible outcomes in larger sample spaces or those formed by complicated events. When an outcome of an experiment is composed of a series of events, the multiplication rule gives us the total number of outcomes. Okay, so multiplication rule of counting, you can see it there. We will see it, I believe, in action, so that will be a little bit easier for you to understand. Jackie is in a nursing program and is required to take a course in psychology and one in physiology, A and P, next semester. She also wants to take Spanish too. There are 2 sections of psychology, 2 of A and P, and 3 of Spanish too. How many different class schedules can Jackie choose from? Assume that the times of the sections do not conflict. What do you think? How many different possibilities are there? Okay. So if we use the rule that they just talked about, creating a class schedule can be looked at as slightly like an experiment with 3 events. You have 2 possibilities for psychology, 2 possibilities for A and P, and 3 possibilities for Spanish too. So if you use the multiplication rule, the total number of class schedules possible will be 12. 2 times 2 times 3. Okay. If you don't believe me, you can sit there and write out Psychology Section 1, AP Section 1, Spanish 2, Section 1, And you keep going until you've exhausted all 12 options, and you will end up with only 12. After that, you will start repeating. But if you don't believe me, you may feel free to do so. All right. A tree diagram gives a visual display of the total number of outcomes of an experiment consisting of a series of events. From a tree diagram, we can determine not only the total number of outcomes, but also the individual outcomes. Okay. This is why I suggest you do this first and then come back to the other ones. I just feel like once you have these techniques down, it will really help you kind of see what you're working with in the other situations. So you can at least get answers using different techniques and then master the technique that they want. Using the information from example 9, let's make a tree diagram that shows all the possible course schedules for Jackie. Figure 4-6 shows this tree diagram. Okay. So here's Jackie sitting at her computer wondering what courses to take. She can take section 1 or she can take section 2. Once she decides which psych section to take, then she can decide if she wants to take section 1 of A and P or section 2 of A and P. But she has it from 2 different nodes. Once she figures that out, she then can figure out which section of Spanish 2 to take. And then you just count them up. All right. So there's your proof that it's 12. I highly recommend when you're making your tree diagrams that you start from the lower option and work your way to the higher. Did you see how they went from 2 options and 2 options to 3 options? You want to do that for the organization. If you do it the other way, it's not going to give you a wrong answer, but then it's basically going to be like starting a tree, the tree ridiculously explodes, and then the tree starts to slim back down. It's just going to be very, very tight and confusing for you. All right. We don't need to discuss that. Okay. So this is an option kind of showing you if you use psychology section 1, and then you can split it into A and P section 1 and 2, and then 1, 2, and 3 for Spanish 2. It's just a different way of showing it. Obviously, that only shows you half of it. All right. The other 6 schedules can be listed in a similar manner, except they begin with the second section of psychology. Okay. Factorial notation. For a counting number n, 0 factorial is equal to 1, 1 factorial is equal to 1, n factorial. Have you guys seen factorials? I'm hoping you have, but here's another example of a regular. Okay, so if we want to find 5 factorial, we take 5 times 4 times 3 times 2 times 1. Okay. If we wanted to find 10 factorial, and this is why the calculator is nice. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Now, eventually, you will be working where you will take something like 10 factorial divided by 5 factorial. So what you can realize is that you would have 5 factorial, and then you also have so if we write this kind of a little bit nicer, you would have 10 times 9 times 8 times 7 times 6 times 5 factorial, and you can cancel out the 5 factorials. Okay. So then you only really need to worry about this one. So you always want to try and minimize the numbers that you're working with, but you can't just delete whatever you want. You have to make sure that it makes sense. All right. That is what a factorial is. All right. We have considered the number of ordered arrangements of n objects taken as an entire group. But what if we don't arrange the entire group? Specifically, we considered a dinner party for 8 and found the number of ordered seating arrangements for all 8 people. However, suppose we have an open house and have only 5 chairs. How many ways can 5 of the 8 people seat themselves in the chairs? Okay. The formula we use to compute this number is called the permutation formula. As we see in the next example, the permutations rule is really another version of the multiplication rule. So we're going to take n factorial and divide it by n minus r factorial, where n and r are the whole numbers, n being greater than or equal to r. Another commonly used notation for the permutation is NPR. All right. So this is kind of where most other stats classes, like if you were taking a high school stats instead of a college stats, they get the permutations and combinations, but they get to it more like at the tail end. You guys are getting it kind of at the beginning because we have so much more to cover. If you can figure out a way for you to understand when to do permutations versus combinations a little bit easier, then you'll have an easier time with this. Let's compute the number of possible ordered seating arrangements for 8 people in 5 chairs. All right, so let me get my marker out. Okay, so we are going to do NPR. N is our number, so we have 8 total guests. So 8 permutation 5 would be 8 factorial over 8 minus 5 factorial. So that's 8 factorial over 3 factorial. So now I can work this out to be 8 times 7 times 6 times 5 times 4 times 3 factorial over 3 factorial. They cancel. So you just have to figure out what 8 times 7 times 6 times 5 times 4 is. And that will be the number of permutations or number of combinations. I try not to say combinations, but they're also combinations. They're just a different way of finding it. Now, what they chose to do is they did the whole thing. I like to eliminate. All right. So there are 6,720 ways that these 8 people can rearrange themselves in seats of 5. All right. Here's another way of looking at it. Here's chairs 1 through 5. Chair 1, any of the people can take chair 1. For chair 2, you have 7 people remaining. Any of those 7 can take chair 2. 6, 5, 4. Right? You kind of understanding what's going on with this? In each of our previous counting formulas, we have taken the order of the objects or people into account. However, suppose that you are a political science class. In a political science class, you are given a list of 10 books. You are to select 4 to read during the semester. The order in which you read the books is not important. We are interested in different groupings or combinations of 4 books among the 10 on the list. The next formula tells us how to compute the number of different combinations. So we would just do 4 or 10C4, I believe. Yes. Okay, so you can write that down and I will work on writing this out for you. So you would have 10, because that's the number of overall books. 4 is the number you have to read. It's going to be 10 factorial, 10, 4 factorial, 10 minus 4 factorial, which ends up being 10 factorial, 4 factorial, 6 factorial. So now we can do 10 times 9 times 8 times 7 times 6 factorial. We have 4 times 3 times 2 times 1 times 6 factorial. The 6 factorials will cancel. 4 cancels with the 8. 2 cancels with the 2. 3 cancels with the 9. So we basically have to take 3 times 7, which is 21, times 10, which will be 210 different combinations for how you would read your 4 books. If you don't believe me, we can check it out on the next page. There you go. A very blurry 210. Okay. All right. You can use combinations and permutations on your calculators. Look it up on how to do it. I don't know every single calculator you guys have, so I cannot just sit here and tell you where to look. Just kind of use Google, YouTube, whatever you want to use. Figure out how to do it. Fine by me. As long as you're putting this stuff in the right places, you should get out the correct result. I would just do it by hand. That's me. At least writing down the factorials. Then you can do the multiplication by the calculator. All right. This is kind of just the procedure. You can look at it if you need to, but you should already have this information down. And that is that. That is section or chapter